Experiences are what people love the most about travel. That's why they love Viator. They have over 300,000 bookable experiences and something for everyone. Plus, their travel experiences have millions of real traveler reviews, so you have the information you need to book the best activities for your trip. Download the Viator app now and use code Viator10 for 10% off your first booking in the app. One app, over 300,000 travel experiences you'll remember. Do more with Viator.
Hello once again. Thank you for joining us on Space Nuts, where we talk astronomy and space science every week. I'm your host, Andrew Dunkley. I hope you're well. Coming up in this edition, Indestructible Asteroids. Yep, they've got some samples. They've hit them with a hammer and nothing happened. And we're talking asteroids that are made of rubble, but it turns out to be more like reinforced concrete. We're also going to look at machine learning or artificial intelligence for the discovery, maybe, of extraterrestrial life. That's coming up. And we're going to answer some questions about gravity and astronauts. What happens when they're going maybe from here to Mars? What's the gravity like compared to orbiting the planet, or lack of there? Also, how is a light year measured? Very carefully. And what pushes rockets in space? We will tell you all of that if we can. Maybe we won't. Coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me, as always, is his good self, Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. And just like those astronauts, I feel good.
Oh, that's good. Me too.
Whoever they are.
Yes. Now, I know last week I sort of told you what I did on my break, which was not the good stuff. The good stuff was that Judy and I went to New Zealand.
Yes.
And we went through Milford Sound and Dusty Sound and the other sound that I could never remember the name of. Very quiet places, despite being called sounds.
Sound of silence.
And yeah, but how amazing. You know what I didn't bet on, and I should have? Seeing snow in January.
Oh, right. Yeah. Well, they've got glaciers there. So
yeah, I know.
Ice all year round. That's right.
I saw it. It blew my mind. What beautiful things they are.
Yeah, they are. Yeah.
In fact, only two of them are sounds and one's a fjord, apparently.
I don't know the difference.
But they call it.
Yes.
I think a sound is you can go in one end and come out the other.
Yeah, certainly a fjord.
Whereas a fjord just sort of ends and you have to turn around and come back.
Yeah, there you go.
I think
that sounds
anyway,
right. Sounds right to me.
Milford Sound, which is the most famous, is technically a fjord.
Oh,
which was gouged out by a glacier.
Yes, that's right. They are there.
One of the things, and this is sort of space sciencey. One of the things they told us about those parts of New Zealand is because of the pressure of billions of tons of ice pushing the structures down, they're still experiencing rebound.
Yeah.
So the water line keeps changing.
Mm-hmm.
And you can see evidence of it where there's no vegetation, like, maybe 30 centimetres from the vegetation line to the water. And I thought it was tidal. But no, they say it's the rebound effect. The ground is lifting, bouncing back. Fascinating.
Similar things happen in Greenland.
Yeah. And we went to Dunedin and drove up the steepest street in the world, which was, I'm just trying to think of the name of it, Boland Street, I think. Actually, I should look it up. Steepest, should remember when I looked this up last night. There it is. Steepest street in the world, Baldwin Street in Dunedin.
Very good.
It has a maximum claimed angle of 35 degrees.
Oh, yes, that's better than 1 in 3.
Pretty hefty.
Yeah.
Pretty hefty.
Yeah.
It's become a major tourist attraction, but a lot of people were walking up it. I could have done that.
Of course.
But we were in a taxi, so I'll let him do it.
Yeah.
And we visited Christchurch, and it looks like a brand new city after the rebuild from the earthquake 11 years ago.
Yep.
Looks brand spanking new, everything. And you'll be interested to know that they've redone the coding for building and construction. The foundations need to go down 30 metres.
Oh, gosh.
They need to be built so that the buildings aren't touching each other.
Yeah.
And they're only allowed a certain height so that they can, everything's got to be able to sway. Everything's flexible so that they can survive a Category 8, a level 8 earthquake on the Richter scale.
Richter scale,
8.2, I think. And then, fascinating. They have a museum there for the earthquake, and we went through it. It's just extraordinary. I highly recommend it if you ever get there. Wellington, Bay of Islands, Tauranga, and we spent 4 days in Auckland for our wedding anniversary. And I hate to say it, Fred, but we did it again. Every time we go somewhere and we come home, there's a natural disaster. And a week after we were in Auckland, they had that torrential rain. They had like a year's worth of rain in an hour and severe flooding. People at the airport, where we'd been a week before, one plane landed and they had to spend the night in the plane because they couldn't get to the terminal because of the flooding. It's just unthinkable.
Incredible, isn't it? Really astonishing.
And sadly, a few deaths. So thoughts and prayers to the people of Auckland, because I know they've had more rain since then.
Yeah.
And it had been raining before we got there. We went. We did a day trip to Hobbiton. You know, the village they built for the hobbits in Lord of the Rings.
Yes.
Went and saw that, and it was drenched, absolutely drenched. But I just wanted to let people know about that holiday, because that was part of the reason I was away so long, was because we spent 3 weeks over there. Gee, it was great fun. We had an absolute ball.
New Zealand always
place.
is. It's the times I've been there, I've thoroughly enjoyed it. And you don't have to be there more than a few hours before you can actually understand what people are saying to you, do you? It's sort of...
It's not that bad.
It probably doesn't sound that bad to you as an Aussie, because you're one step removed from that.
I suppose it's like comparing American accents to Canadian. They sound pretty much the same to everybody except the Americans and the Canadians.
Yeah, no, they're quite different. But yeah, it's always a delight going to New Zealand, and the people are delightful as well.
Oh, it is.
Yeah.
I'll tell you something, just by the by. I know I'm talking too much, but that's why I get the big bucks.
That's what you do. Yeah.
Part of that trip was a cruise, which enabled us to do the sounds and whip around the bottom of New Zealand and visit all those amazing places. Every night for dinner, we sat with the same group of people, and one of them was a former Winter Olympian.
Oh,
yeah,
interesting.
I said, "How did you go?" He said, "Oh, we got disqualified." I said, "Why?" He was a bobsledder.
Okay.
And he was for the American team. He said one of our guys fell off.
Oh, well, yeah. It's not a good look, is it?
But what a nice guy. What a really lovely guy. Gee, it was good to spend time with him and his wife. And he was originally a sprinter, and he got into bobsledding and got into the Olympic team at I think it was Calgary. He was at Calgary Olympics.
It's quite a while ago.
Back in the 80s, was it?
Yes, that's right. I hope you told him about Space Nuts.
I did.
Astro bobsledding that we do.
Astro bobsledding. Now, that would be great fun. Yeah. I'm sure we could. Anyway, that, a potted edition of our holiday. If you want to see the holiday snaps, they're on my Facebook page and Instagram.
Of course.
Now, let's do what we're supposed to be doing and talk about rubbish. And rubbish being the form of indestructible asteroids that are made of rubble, but as it turns out, they are the strongest and most difficult to destroy things in the solar system, by the look of it, to a certain degree anyway.
That's right. So this research, Andrew, it's fascinating. It's got a strong Australian flavour as well. Much of this has been done.
Strong and indestructible.
Yes, of course. Absolutely. It comes from Curtin University School of Earth and Planetary Sciences. And that particular institution was fortunate enough to get some of the particles that were returned by JAXA, the Japanese space agency, from the asteroid Itokawa. Sorry, mispronunciation there. Brought back by Hayabusa. The first one, I think, went to Itokawa. There have been 2 of those spacecraft. Anyway, it's a sample return mission, brought back these samples of an asteroid which we know to be just a pile of rubble, an orbiting pile of rubble. How do we know that? Because half of it is empty space when you look at the density, which you can do by measuring the gravitational field as you orbit around it. So it is a rubble pile asteroid, and we think there are many rubble pile asteroids, that they are quite common. And what causes them, Andrew, is, at least in the theory, is that if you imagine two solid asteroids coming together, they smash into one another and break up, and those fragments just collect themselves by gravity into a new rubble pile asteroid. Because
like a conglomerate.
yes, that's right. Only without any kind of concrete holding it together. It's just held together by its own gravity. So the expectation from what we know about rubble pile asteroids is that they might not be very tough, that, if you bash into them, they'll fall apart. And I think that is probably true, but there is an effect that comes in to play, which doesn't come into play with a solid asteroid. So if you clout something with clout a solid asteroid with another asteroid, for example, they break up. They react in the same way as you intuitively think if you throw two stones at each other and they smash up together.
Yep.
But with the rubble piles, and there is a lovely description actually by Fred Jordan, another Fred, who's a professor at Curtin University School of Earth and Planetary Sciences. He says it's like a giant space cushion, and cushions are good at absorbing shock. So yes, the fact that it's a pile of rubble, you bang something into it, and since half of it is empty space, it just absorbs the shock and stays together, rather than, as you'd expect, intuitively perhaps, flying apart. And so what these scientists have done with I think they had three fragments from asteroid Itokawa that came to them from the Hayabusa mission. They looked at the structure of these fragments, the crystal structures that are there, and also the atomic content of these fragments. So with the structure, they were looking for evidence of deformations in the crystals that would have been caused by the impact that created that rubble pile. And then they could date the samples themselves by, in fact, it was the decay of potassium into argon that they measure. It's a nuclear decay. And what they get for the age of the asteroid is that it was formed from a collision 4.2 billion years ago. And that contrasts with the average age of the solid asteroids, which is typically, more like 0.42 billion years. In other words, less than a billion years, something like 420 million years. They suggest that this is evidence that says that rubble pile asteroids last a lot longer than solid asteroids. Of course, solid asteroids are what form rubble pile asteroids, but so one leads to the other. But it is counterintuitive, isn't it? You'd expect the solid ones to be the old grandfathers of the asteroid belt,
and be tough.
Yeah, and be tough, and these rubble piles just to be fleeting things that might fall apart at any time. But it's quite the other way around. And
fascinating.
In fact, Fred Jordan made this lovely comment. We were really surprised. I can relate to that. He says, that's really, really old, and I'm sure some of my colleagues are not even going to believe it. This is the age of Itokawa. So that work has now been published in Proceedings of the National Academy of Sciences. Really excellent stuff. There is another comment from Fred Jordan, which relates to what you'd do if one of these things was threatening the Earth.
Yeah, and that is the problem, because if they're so tough, what are we going to be like? We can't get Bruce Willis to go up there and destroy it.
No, that's right. It's always a bad idea.
Yeah. So what are we going to do?
So we've had the DART test, which is great. The DART test last year demonstrated that, yes, a uh, uh, an impacting spacecraft can actually affect the orbit of a small asteroid. And that's great to know, because that would have been very disappointing if nothing had happened. But what they're suggesting for the same sort of thing with one of these rubble piles, and this again is Fred Jordan, he is suggesting that a nearby nuclear blast might do the trick. Not one that's aimed at blowing the thing up, but a nearby nuclear blast.
Creating a concussion.
Yeah, creates a shockwave, which would push the asteroid out of the way. I
never thought of that, and yet that seems so simple.
It does. I think it might be tricky to execute, but that's certainly his thinking. And I think he's clearly working on this sort of thing as well. It's really quite a remarkable story that you can get, something like that out of a few grains of dust from brought back by a Japanese spacecraft.
Indeed, yeah, and learning so much. So does that mean that these kinds of asteroids are more the norm now?
I think that we're talking about sort of 50-50-ish distribution,
right?
But they're certainly of interest. And the reason is pretty well encapsulated in the title of Fred Jordan's paper, which I'm sure you've noticed. It's a lovely title: "Rubble Pile Asteroids Are Forever."
Yeah, that's clever. Yeah. This one's rather big, though, isn't it?
Half a kilometre across. Yes. And I think that's fairly typical of these things. They're usually less than a kilometre. And as you'd expect, they're made up of the debris of a former collision, and so some of that debris would have gone somewhere else probably. So even if it's two big asteroids that collected each other,
that's sort of getting up there into the realm of major damage.
If it hit the Earth, yes,
it
will be. Yeah. It will be very significant.
That'd be like continental destruction, wouldn't it?
It would, and it would be a good idea to see whether the nuclear blast trick would work to push it out of the way. So maybe that's the next thing, a new dart test going to a rubble pile rather than a solid asteroid.
Yeah, that's probably not a bad idea. Yes, you can find out more about that particular story, if you like, at phys.org, the website. Very great source of astronomy and space science. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Fred, the search continues for extraterrestrial life. You and I have discussed this many times, and there are lots and lots of processes going on to try and discover them, whether it's spectrum analysis of exoplanets to listening for radio signals. But now there might be a new tool in the box.
Indeed, there might be, which looks as though it's actually going to be quite interesting. And that new tool is AI, artificial intelligence, because what's happened in the past with the things like the SETI search for extraterrestrial intelligence, which is a very broad-based project that's been going for 60 years, I think now, to analyze the signals that normal radio telescopes gather when they are doing their normal work in mapping the skies in radio frequencies. So often the SETI experiments ride on the back of other projects which are looking for natural radio signals, but the SETI Institute and other other SETI enthusiasts, professional enthusiasts as well as amateurs, they are riding on the back of that. They're sifting through the signals to look for any sign of something that might be artificial. And that's been going for a long time. So what's happened is that the algorithms that were developed many, many years ago, actually going right back to the earliest days of computers, when you use those algorithms with the kind of data sets that we have now coming from radio telescopes, where you're talking about petabytes rather than, megabytes or kilobytes, that these algorithms are not probably the best suited to those huge volumes of data. And so some work that's been done actually by an undergraduate student, which is always admirable, seeing somebody early in their career producing pretty neat work like this, This is a student at the University of Toronto, along with colleagues from the SETI Institute itself, and Breakthrough Listen, which we've talked about too, other institutions. What they've done is they've used new artificial intelligence algorithms to comb through these data using what they call a deep learning technique. And what they've done is actually taken a data set basically of signals from nearby stars, which is something that's been combed through already and which didn't really show up anything interesting. Signals of interest is what they're called. They've actually done it with a new artificial intelligence algorithm and uncovered 8 signals of interest, which hadn't been seen before. Now, I guess you and I, when we think of a signal...
Should I say, wow?
Yes, that's right. That's what I was going to say. When we think of a signal of interest, the first thing we think of is wow, the famous wow signal of the 70s, which has never been really understood.
Resolved.
Resolved. It's, but these are, I think, are much lower intensity, but they've found something that's of interest. And I'll say why they're of interest in a second. But just the numbers are really quite nice. Peter Ma is the name of the undergraduate student who did this work. He said, we had searched through, in total, we'd searched through 150 terabytes of data of 820 nearby stars on a data set that had previously been searched through in 2017 by classical techniques. That's the old algorithms, but labeled as devoid of interesting signals. So they searched through it again and found these 8 previously unidentified signals. And what Peter goes on to say is we're scaling this search efforts to 1 million stars today with the Meerkat telescope and beyond, Meerkat being the equivalent of the Australian Square Kilometre Array Pathfinder over there in South Africa. We believe that work like this will help accelerate the rate we're able to make discoveries in our grand effort to answer the question, are we alone in the universe? So
it is amazing.
It is. It's great stuff. So what they did, the data, by the way, that they re-examined was taken with the Greenbank telescope, West Virginia. It's a very famous radio telescope, and applied this new algorithm to it. And what they then did was looked at what the algorithm spat out in terms of things that were interesting. And they noted that these newly detected signals had a number of characteristics which essentially teased them out from the others. Those characteristics were, first of all, that they're narrowband signals, which means that they cover only a few hertz in frequency, hertz being 1 cycle per second, whereas many of the signals that we receive from natural phenomena are broadband, although not all of them are, but many of them. So these were narrowband, and that's kind of what you'd expect. They had drift rates, and by that I mean their frequencies change with time, and that is what you'd expect if you get a signal that's coming from, say, a planet orbiting around another star. Because the Doppler effect, as that planet goes around the other star, the Doppler effect will change the frequency. And they found...
Just like the sound of a siren?
Yeah, that's right. Yeah, that's the one. Yep, it's exactly that. Okay. And so that suggests that these signals were real in the sense that they came from, they came from something outside the immediate vicinity of the observers, because a signal that was, for example, radio interference from somewhere would not normally change like that. Although I do remember that one of the candidates found from the Parkes Observatory, it's a couple of years ago now, was eventually debunked as being extraterrestrial origin, even though it did have a drift in frequency. It was still found to be terrestrial. Anyway, the ones that they discovered do have a drift in frequency, which suggests that they might not be terrestrial. And of course, they only appear when you're pointing in a particular direction. So that's to say, if you turn the telescope somewhere else, you don't see the same signal. And that's actually, again, unlike radio frequency interference that is generated by ourselves, humans. that interference would usually be there whether you were on or off target, because it's kind of local to the observatory. So it's a very nice piece of work. There's a nice comment from Cherry Ng, who's actually one of Peter Ma's research advisors. And actually, she's at the SETI Institute and the French National Centre for Scientific Research. Says these results dramatically illustrate the power of applying modern machine learning and computer vision methods to data challenges in astronomy, resulting in both new detections and high performance. Application of these techniques at scale will be transformational for radio techno-signature science. Lovely stuff.
Yeah. I wonder what they do next. I mean, how do you take it to the next level and analyze these signals to see what they might be?
Yeah, so what you do is go back to that bit of the sky where these signals were found, because they're in specific places in the sky. You go back to them and see what you can see. And I think they've done that. I've not seen anything yet.
Yeah. That's because the radio show ended on that planet.
Well, maybe that's right. Yes, maybe.
Didn't get renewed after Christmas.
Yeah.
That's what happened.
Or they all went over to fibre or something like that. You know?
It might be.
Yeah.
Yeah, that'd mess things up, wouldn't it?
It does a bit, yes.
you think about, like we've talked about it before, that there could be advanced civilizations on planets in circumstances where they're not capable or not necessarily, don't necessarily need to transmit.
Yep.
Maybe they live underground, or maybe they live in water. Or
yes, that's right.
You just don't know, do you? So, yeah, there could be many out there that are just not discoverable.
That's
under
correct.
The circumstances.
That's certainly one of the considerations that SETI people take into account. Yes.
But the more we look, the more the odds are we're finally going to hit the nail on the head.
Well, maybe so.
But I think before that, we're probably going to dig a hole in an ice moon and
there's that too.
Grab some krill.
Yeah, I'll look for the krill. That's right.
Yeah,
follow the water.
Krill, there are whales.
There'd have to be, wouldn't there?
Yeah, I'm not sure krill. That's too advanced.
Yeah, probably. Probably.
We watch with interest. You know what really excites me, Fred? Not just this particular storyline, but the fact that they can take old data and apply new technology and redo studies and find interesting things to announce. There's been so many new papers in recent times that have been published based on old data that's been reanalyzed. Oh. And I really think that's extraordinary.
Yeah,
that they can read between the lines with new technology and go, well, as a matter of fact,
yes,
we just discovered this from a 1950 analysis, or something like that.
No, it's true. And it highlights the value of data archives, because you've got to keep all this stuff. And even the old photographic plates taken in the 19th century, many of those have been digitized anyway, but the ones that haven't could still contain information that might be of use. For example, in the position of an asteroid that's recently been discovered, where what you want to do is find observations over as long a period as possible to refine the orbit of that asteroid and tell you where it's going to be. So might be very important one day.
Yes, indeed. And once again, I think this one was a phys.org story, so you can chase that up there if you're interested in learning more about machine learning and AI to help us find extraterrestrial life.
You're listening to Space Nuts, the podcast about astronomy and space science with Andrew Dunkley and Professor Fred Watson.
Okie dokie, Fred. Guess what? It's time to get the audience involved, because we encourage questions, and we start, as I mentioned last week, we're starting from scratch. So if you'd like to send some questions in to us, by all means do, text or audio. If you do send us audio questions, please make sure you tell us who you are and where you're from, because we love to know that stuff for no particular reason, except that we're stalkers.
Well, now makes it sound good, doesn't it?
It does, yes.
People are listening all over the world.
They are.
Both of them.
It's because that's you and me.
Yes.
Yeah. Now, our first question comes from Annette. I love this question, and I think Annette's asked us a question before. But I like her thinking here, and I can understand why there might be a bit of confusion.
Hi, my name's Annette from Manchester in the UK, and my question's about gravity and how astronauts experience it. So, my understanding is that those astronauts inside the International Space Station are falling towards Earth, as is the space station itself, and that's the reason why they appear to be floating inside it, because it's all falling towards Earth with feeling the effects of the Earth's gravity. So, what of astronauts heading to the moon or even to Mars? Do they feel the effects of the Earth and the moon at, say, for example, the beginning and the end of their journey? Or do they have a floating effect, as it were, throughout their whole journey from beginning to end? So, in fact, is it the sun that is the main reason for the gravity effects? So, my question really is, can they stay in their seats easily, or do they need seatbelts to kind of keep them in there, as it were? I hope that makes sense. Love the show and looking forward to the answer on my question. Thanks very much.
Thank you, Annette. Great question, because, yes, we do know that orbiting the planet, you're just constantly falling, and therefore you are floating as a consequence of that, 0G. But when you're traveling to another satellite like the moon, or traveling to, say, Mars, which will happen in the not too distant future, is it the same effect? Is it different? Are there times where there are variations in the 0G effect?
Yes, there are, but they're not due to natural causes, because whenever you're moving along an orbit, and you're always moving along an orbit of some kind, you're in this state of free fall, which means you're weightless and your rocket is weightless. The time when you feel your own weight is when you fire the rocket motors, because that provides an acceleration to the spacecraft. And that's to put you into the right velocity and direction, the right orbit to go to wherever it is you're going to. So, for example, think of it this way: if you've got astronauts going to the moon, then what you do is perhaps they start off in orbit around the Earth, in which case they're still falling towards the Earth, exactly as Annette said. That's exactly what's happening. You fire your rockets to inject them into an orbit that will carry you to the moon, and it's still an orbit around the Earth, but it's now a very elongated one. But once your rocket's cut out, you're still in free fall. Basically your motion is dictated by the gravity of the Earth, unless you've achieved this 11 point whatever it is kilometer per second that allows you just to keep on going. And then you're in free fall. But what would happen then is you'd go into orbit around the sun, and you would be in a free fall around the sun, which means that in its own peculiar way, you'd be falling towards the sun, because the acceleration, it depends how much velocity that you've been given. The spacecraft out in deep space, and think of New Horizons, which has gone past Pluto and past Arrokoth, and is on its way out into interstellar space. That's still feeling the gravity of the sun, but the gravitational pull of the sun is not enough to slow it down, so it will leave the gravitational influence of the sun. And the astronauts in it, if there were any, but the microbes that are on it probably, they are weightless. They don't feel weight because they are just moving in this orbit in a gravity field, but moving with enough velocity that they're not being pulled back. It's a bit slightly garbled explanation, is that? But that's kind of what's happening.
Yeah. So what are you orbiting when you go to Mars?
Yeah. So that's, I was going to say, so in the situation where you go to Mars, which is what I meant to say in the beginning, but forgot to, is your spacecraft, when you leave the Earth, you will use your rockets to put it into something called a Hohmann transfer orbit. Hohmann, Hohmann, named after an engineer, actually, Professor Hohmann. And that is just a long ellipse that is part of an orbit that both intersects the orbit of the Earth and the orbit of Mars, and it transfers you from one to the other. I wrote quite a lot about this in Space Warp, actually. There's a lot about this kind of space navigation, including one of my cartoon diagrams, showing this phenomenon perfectly. So you're still in orbit, but you're now in orbit around the Sun. You're in a long, elongated orbit, taking you from the Earth's orbit to Mars's orbit. But in doing that, you're in orbit around the Sun. And then when you get to Mars, you've got to slow down so that you don't just fall back again inwards towards the Earth's orbit.
I see. So, you're intentionally creating this orbital effect, but you have to interfere with it to inject yourself into a landing pattern.
You do.
Your destination.
That's right. You've got to tinker with it. You've got to fire your rocket motors. Hang on.
You're right.
Yeah, I'm just going to get the book, see if I can find the picture for anybody who's looking.
So
here we are.
So I suppose when you're calculating what you need to do, you have to take all this into effect.
Which is why you need modern computers. Now, I don't know whether you can see this, Andrew.
I can.
But that is, see where the start banner is there? That's where you inject yourself into this transfer orbit, and there's the spacecraft on its way to the orbit of Mars. If you didn't slow down when you get to Mars, you just keep on going and coming back to intersect the Earth's orbit. But the trouble is the Earth's not there anymore. So you're not actually coming back home. You're coming back to the Earth's orbit, but the Earth's somewhere else in its orbit. So it's a bad scenario. If you forget to fire your braking rockets when you get to Mars, you're in big trouble.
Yeah, or if they don't work.
That's right. So it's all dictated by, orbital mechanics. It's the way it all goes.
Amazing.
Space Warp. 14 pence from your local bookshop.
It's still hard to comprehend, though, isn't it? That everything you do in space is in orbit.
Yes, that's right. That's once you grasp that, it's not like a flight, in the Earth's atmosphere where you can go in a straight line, borne up by the atmosphere. That's the force that's holding you up there. In space, there aren't any straight lines. It's always an orbit of some kind. Sometimes it's a very elongated one, in which case it's almost a straight line, but it's never quite a straight line. It's always dictated by the gravity of the sun, basically.
Okay, wonderful question. Thank you, Annette. And when you said planes fly in straight lines, it reminded me, I didn't tell you this about our New Zealand trip. When we came home, we flew, we took a Qantas flight from Auckland to Sydney. The very next flight, the exact same flight, was the one that got into trouble the other day with engine failure.
Yeah, right.
Gosh, we're dodging some bullets.
Yeah, makes me worry when I get on a plane on Saturday. How many of those?
I actually tried to find out if it was exactly the same aircraft, but the timing was wrong. So it wasn't the plane we were on, but it was the next one, same kind of plane, a Boeing 737.
Yep.
But I got a survey from Qantas afterwards saying, asking me questions about the flight, and it said, "What did you think of the plane?" I said, "Well, it's a short trip, so you give us the old rusty ones, don't you?" Because they do. Pretty ancient. Yeah. I think I saw Leonardo da Vinci's graffiti on the toilet wall. Honestly.
That was Qantas decor.
Yes.
not graffiti.
I love them. I do.
Oh, dear. Yep.
Now, thanks, Annette. Let's go to our next question. This comes from Ross, who I'm going to guess is an Australian.
My name is Ross Simon. Just wanted to know what with space-time being relative, how is a light year actually measured? What's the year? 365 days, or what's it supposed to mean in terms of when it says that it's going at number of light years away?
Thank you, Ross. I don't know what part of Australia you're from. I can't pick dialects in this country. Some of them I can, but that one I couldn't. But thanks for your question, Ross. Ross Simon, wasn't he a famous ABC News reader?
Might still be.
Yeah?
Yeah.
I think it was Ross Simons.
Yeah,
Not sure.
I think
But,
it was Simons too.
Had a great voice.
Yep.
Fabulous voice. How is a light year measured?
So is it
Laser. They use laser.
It's a light year is just a tool that we use to give us a measure that's easier than trillions of kilometers.
Yeah.
We don't measure light years. I'm sorry to fess up on this, but astronomers do not measure light years.
Parsecs?
Yes, we do measure parsecs. So a light year is the distance light travels in 1 year, and it would be probably a tropical year of 365.25 days. That's the standard year. But the speed of light being constant, and no matter what you do with space-time, the speed of light is constant, 300,000 kilometers per second. That lets you work out the fact that a light year is 9.5 trillion kilometers. And that's really all it's about. It's just a convenient way of expressing distances, but we don't actually measure light years because you can't do it. You know, you can't have somebody with a laser at one end and somebody with a stopwatch at the other. It just doesn't work that way. What we do measure is the angle of parallax of an object, which means that you look at a star, for example, and measure its position when the Earth is on one side of its orbit, and then measure it again when the Earth is on the other side of its orbit, about 6 months later. And what you get is an angle, and you can convert that angle to the distance of the star. And the term parallax is what we mean. Parallax is the angle that the Earth's orbit subtends at the distance of the star. It's actually, yes, it's on your shelf, isn't it?
There it is.
Yes, I can see
You're
it.
spruiking your book. There's my.
Yeah.
I've actually done 3 chapters of the audio version.
Oh,
now.
great. That's
Of Parallax.
Great. Parallax, yeah.
Yeah, I've had time.
Well, you would have had. That's excellent. Anyway, Parallax, a great book by Andrew Dunkley, but also a term used to represent the angle that a star makes. That the Earth's orbit makes from a star. And an angle or a star that has a distance of 1 parsec means its parallax is 1 second of arc. And second of arc, of course, a tiny angle, 1/3600th of a degree. I've simplified it a little bit there because in reality, 1 parsec is the distance of a star whose for which the radius of the Earth's orbit subtends an angle of a second. It's not the full orbit, it's just the radius of the Earth's orbit. So from the sun to the planet, when it's at its most extreme position as seen from the star, that's what the parallax angle of 1 second is. It's about I always get this wrong, 3.23, I think, light years is one parsec. You can look it up. I'm sure you
3.26.
Oh, no, nearly there. Anyway.
I'd already looked it up.
Yeah, so 3.26 light years is one parsec. And so we measure parsecs and then convert it to light years because everybody can understand that.
3.086 times 10 to the 13 kilometres.
A parsec, yes, that would be right.
Yeah. I knew that off the top of my head. You didn't hear, that wasn't a mouse click.
Yeah. It's 3.26 times 9.5 trillion. And that must give the answer to what you just said.
Yes.
You worked it out in your head.
I didn't. Not remotely.
No.
Hope that answers your question, Ross. We'll do one more quick one before we wrap it up. This is an email that came from Jim. And he said, long-time listener, but first question, if I may. If space is a vacuum, what is it that a rocket pushes against in order to change direction? Research tells me that space contains on average 5 atoms per 1 cubic centimetre, and in interstellar space between stars contains around 1 atom per 1 cubic centimetre. Surely this would be enough to wouldn't be, I think he's trying to say, wouldn't be enough to enable efficient rocket use. Could it be dark matter?
It's far more straightforward than that. Rockets don't push against anything. They don't need something outside to push against. What you've got with a rocket is the combustion chamber, which is where the fuel and the oxidizer are mixed. So you've got this essentially a bottle with very high pressure inside it, and it's almost like, well, it's a pressure chamber. In fact, if you imagine it with the nozzle shut off, it becomes a pressure chamber. You've got this constant explosion taking place. That now, like in that condition with no nozzle, this pressure chamber would just sit on your desk or wherever you put it, because all the forces are balanced out. The expansive force is balanced on one side by one pushing on the opposite side. So the forces pushing on opposite sides of the combustion chamber balance each other out. But then you take the plug out and you've got an exhaust nozzle. And so what then happens is the exhaust comes out of the hole, of course, but there's nothing to balance the force on that side. And so that unbalanced force is the thrust of the rocket, which is the force that drives it forward in the opposite direction to the exhaust. So it's just the fact that you've got an unbalanced force inside the combustion chamber that lets the rocket work.
Okay. Does not need anything out
Doesn't
there.
need anything. So it means your mod finite rockets work in the same way. So if you took them up into the vacuum of space and lit the fuse, away they'd go, because they work on the same principle. They don't need air.
And jet engines aren't like that, because they need to take in something to create the combustion, to create the thrust.
And in fact, what's happening in a jet engine is that it's being pulled along by the compressor at the front. Often we've got a big fan at the front now in the turbo fans. But in a straightforward jet with just a compressor and a turbine, the force on the axle that connects these two is actually forward, and that's what's pulling the plane along. So it's the compressor is pushing it through the air.
Fascinating. So how does a scramjet work?
The compression takes place just because of the shape of the air intake. You've got it moving at supersonic speed, so that compression's happening there. There is a balanced thrust as well. I'm oversimplifying it. You might notice that jet engines in particular have got a cone at the back with the turbine running round it, and the cone is where the exhaust comes out, and that again provides a pressure point to push the aircraft forward.
It's all very interesting, isn't it?
It is, isn't it? It's great stuff.
I love it.
I wish I knew what I was talking about, Alan.
Yeah, I wish I knew what you were talking about too.
Nearly called you Alan then. I don't know why. Never called you Alan.
I've been called Alan many times. I've been called a lot of things.
Yeah.
Some of them not airworthy.
No. Or seaworthy either.
Yes.
Yeah.
Thank you, Jim. I hope that answers your question. They don't need nothing out there.
No, that's right. There's also a cartoon in Space Warp explaining exactly that.
Yeah, there you go. Sales must be down.
Yes, they are down, yeah.
They peter out, but they don't stop, I've noticed, with books.
I hope not. I've no idea what mine are doing. I haven't caught up with them for quite a while.
I got a royalty the other day for $1.20.
Fabulous.
Yes.
Fabulous.
I don't know where from or what for. I think it must have been an ebook.
Yeah.
But, there was a little burst of interest just before Christmas. So there you are.
Excellent.
I must confess my marketing is lacking. I can't be bothered. No. If I tried hard enough, I might get $2.20.
You buy it. Well, that's right.
Yeah.
Get your act together and you might even get $3.
Yeah, never know. Waiting for the dollar to get a bit weaker so I can get some more US currency going there. All right. Thanks, Jim, Ross, Annette, for all your questions. Don't forget, if you have questions for us, we want them. We're starting afresh, so we need a new batch for 2023. So get on our website, spacenutspodcast.com, and you can hit the AMA tab up the top and send us text or audio questions. And there's a send us your voice message button on the right-hand side of the homepage where you can do the same thing. Don't forget to tell us who you are and where you're from, whether you're sending a voice question or text. It's nice to know. And that's it for another day, Fred. Thank you so much.
So farewell, episode 338. Is that right?
It is, yeah.
Thank you very much.
It's gone so fast.
Yes, it has, yeah. Always good. We'll see you soon.
All right. Thanks, Fred. Catch you in a week or 2 or 3 or 4. Fred Watson, astronomer at large, part of the team here at Space Nuts. And back in the studio, it's Hugh, who's peeling oranges, or is it potatoes? He's doing community service. We'll be back next time. Thanks for your company from me, Andrew Dunkley. Until the next episode of Space Nuts, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.